Hello everyone, welcome to this module. This will be the last module in this course where we'll be discussing about diffusion models. Specifically in this module, I will be discussing about two improvisations on top of DDPMs. One is called the latent diffusion models, the other is called the DDIMs or diffusion implicit models, which are often used in the state of the art, which both of which provides considerable advantage over the naive formulation of DDPM. So let us start with the latent diffusion models. Latent diffusion. These are also oftentimes referred to as the stable diffusion models as well. So there's no algorithmical novelty in latent diffusion models, but at an implementation level, instead of using diffusion models on the data space, diffusion models are built on the latent space of some other encoder-decoder structure. So this is the basic idea of what latent diffusion models is. Let us go through it. Now, the basic idea is to build diffusion models on the latent space induced by another encoder-decoder model. Another encoder-decoder model. So why is this done? The basic idea is that if you consider data like images, they typically lie in a very, very high dimensional space, as we know. So now creating Markov chains and operating with data that is in an extremely high dimension creates a lot of issues, in terms of stability and learning the distribution properly and so on. So instead of that, the idea in latent diffusion models is to operate on the latent space of some other encoder-decoder model that is pre-trained. So given data, so we have been indicating that with x0. So let's say that this is in some RD. Okay. The first step is to learn a latent representation let's call it some Z0. This is in some RK, where K is much less compared to that of D, using an encoder-decoder model. So an example that is typically used for the image dataset is construct a vector quantized VAE or a VQ-VAE that we have seen before, VQ-VAE, to learn a latent space. So we know that in a VQ-VAE, the latent space is deterministic in the sense that given a particular x0, it will give one deterministic vector which is vector quantized. So what happens is that you have an encoder-decoder model there is an encoder and we have a decoder. x naught goes in. This is the encoder and this is the decoder. And in the decoder, we have the data reconstructed, right? X naught cap comes out, and we have some representation of x naught, which we call as z naught. So let E phi represents an encoder. E phi and d theta represent the encoder and decoder function respectively. D theta represent the encoder and decoder functions respectively. So these are pre-trained encoder and decoder functions respectively. Okay. So we have to train the E phi and d theta are trained using the original data x naught, or sometimes it can even be trained using some other data set that is similar to that of x naught. Okay, so it's a pre-trained encoder decoder structure, either using original data or some other data set similar to x naught. Right? We just pre-train it. Then what happens is all the data points in RD, which is the real data space. So let's call them E theta phi and E phi star and D theta star to represent that pre-trained. All the data points in RD are projected onto the latent space via the encoder. So we have z naught given as E phi star of x naught, right? So once we have an encoder trained, we can just take the trained encoder and project the data points, all the data points that we have, onto the latent space. Now what is done is a DDPM is constructed, a diffusion model is constructed on z naught. Okay, on z naught, on rather let's say that on the space of z naught, we construct a DDPM using the space of z naught. Okay, now during inference, to generate a null point, see, note that our final goal is to generate a null point from the distribution corresponding to the real data, not from the latent space, right? During the inference, to generate a null point from Px naught, which is the distribution of the real data. So let us also write it down here. So x naught is in RD. So we have x naught is in RD and it is sampled from Px naught. That is the underlying data distribution that we want to sample from. To generate a point from Px naught, first sample from the latent space, sample a null point from the latent space. So how do you sample a novel point from the latent space? Novel point from the latent space with the denoising or the reverse diffusion. This is because the diffusion model is built on the latent space of data. First sample a novel point from the latent space of the reverse diffusion. So call it Z novel, okay? And X novel, the new point, will be equal to pass it through the pre-trained decoder, pass the novel latent point through the decoder to get the final novel point or the unseen point that is sampled from. So this will be sampled from P of x naught, right? Because the decoder has been learned that way. See, note here that the diffusion model is being trained on the latent space of a pre-trained encoder-decoder, right? The advantage of this is that we are not constructing the diffusion model on a high dimensional data space. Rather, we are constructing the diffusion model on a much lower dimensional compact latent space that we have learned using a pre-trained encoder-decoder model. So most of the currently available implementations are based on this principle, that there is a strong encoder-decoder model that is pre-trained on the given data, and a diffusion model is built on the latent space of the encoder-decoder model. During inference, a novel point is first, since the diffusion model is built on the latent space, it only learns how to generate the latent points from the latent space. Now, once you have a point from the latent space, pass it through the decoder, the pre-trained decoder, to get the point from the data space. So that is the idea. Okay, so this is also called as stable diffusion because it is empirically observed to be much more stabler in generating image-like data sets compared to building a diffusion model completely on the image space or the original data space. As I said, algorithmically, theoretically, nothing changes. You still have the DDPM that is to be built. Mathematically, if you look at it, then x or z doesn't matter. It's just a random variable upon which we are constructing a Markov chain. But from an implementation perspective, latent diffusion or stable diffusion is the process where you project the data first onto the latent space of a pre-trained encoder-decoder and then build a DDPM on top of it. So that's the idea. Okay,